Good morning. This is a brief recap of what we had covered on properties of solutions. I'm looking at our new unit. So the objectives are students will be able to define solute and solvent and identify solutes and solvents in a solution, explain the difference between a dilute and concentrated solution, describe the dissolving process at the molecular level using the concept of random molecular motion, and then explain how temperature, pressure, and surface area affect the dissolving process. Okay, so just to begin, we had the definition of a solution. All right, so a solution is basically what's called a homogeneous mixture of solute and solvent. So homogeneous, homo versus hetero. Hetero means different, homo means the same. So when we're talking about a homogeneous mixture of solution and solvent, mixture. So a mixture is anytime you put different things together. Okay, I could be making a salad. I've got the different types of lettuce. I can have tomatoes, croutons, whatever you want in there. And then you put it together. So it is a mixture because it contains different things. Now there is what is called a heterogeneous mixture. And then you can have a homogeneous mixture, which would be a solution. Homogeneous, homogeneous, tomato, whatever you want to say. I tend to say homogeneous. So homo means the same, so that means your particles or whatever you have is mixed evenly throughout. Now with a salad, that's not homogeneous because what would happen is when you toss or mix a salad, the fact is when I grab a tong full of salads and put it on one plate and tong full of salad and put on another plate, you can't say that they're going to be the exact same mix. You can't say that each person is going to get the exact same number of tomatoes or croutons or the exact same amount of different types of the lettuces. So that is not homogeneous. That's hetero. It's different, heterogeneous mixture. Now with a homogeneous mixture, again, this is a solution. What happens is everything is distributed evenly throughout. So for example, if I take something like salt and I mix it in water and it's dissolved really well, okay, 1 teaspoon of salt, that salt water, is going to be exactly the same as another teaspoon of salt. So as far as the amount of salt that's dissolved in that teaspoon of water is going to be the same as the other teaspoon I pulled out. We're talking about in the same container, all right? Okay, so solution is going to be a homogeneous mixture of solute and solvent. So what is solute and what is solvent? A solute is what gets dissolved in a solution. All right, as I said, this is just a brief review. If you need to pause the video to get things down, please do so. So this is what gets dissolved into the solution, which is a homogeneous mixture where everything is evenly distributed, spread throughout. Solvent is what is doing the dissolving. All right, so when I do something like I put salt in water, the salt is what is getting dissolved into water. The water is what is doing the dissolving. So your solute would be the salt, and your solvent is the water. And in most cases, water is the solvent. You know, if I want to make Kool-Aid, I take my Kool-Aid packet, that powder, and I dump it in water and I mix it up. Again, water is doing the dissolving. The Kool-Aid is what is being dissolved. The same thing if when you're making lemonade and you're putting a bunch of things in water to be dissolved, all right? So that would be solvent again is what does the dissolving, and your solute is what is being dissolved or being spread throughout the water, all right? So examples, here are a couple of examples. We just talked about them. Solution, your homogeneous mixture, solution, salt water, put salt in water, mix it together. The solute is what is being dissolved, salt. And then the solvent does the dissolving, and that's the water. So the salt is being dissolved in the water. And here again is a Kool-Aid, and yes, I spelled it wrong there. It should be with a K. Kool-Aid powder would be the solute, and then the solvent is what the Kool-Aid is dissolved in. Okay, so the water is the solvent, and again, the Kool-Aid is the solute. All right, concentrated versus Concentrated solution versus a dilute solution. So concentrated solution contains more dissolved solute in solvent than in dilute solutions, okay? So concentrated, if it's a concentrated solution, then I'm going to have more salt. I'm going to dump more salt into the water and mix it up, all right? You have more salt dissolved in the water. If it's a dilute solution, you have less solvent, so there would be less salt dissolved in the water, all right? Less particles of salt dissolved in the water is dilute. The more you have, the more solute you have. And I can see that there is an error here. So concentrated is, please correct this. This is, should be more solute, not solvent. So please correct that. So more of the solute is dissolved in the substance or in the solvent, all right? So in the solution, you're going to have more solute. For concentrated, dilute, you're going to have less. On the next page, what we are doing is that we're looking at it in terms of particles. So it says here, what you have is a picture of a dilute versus concentrated solution. You're supposed to use two different colors for water and sugar and identify them in the column. So here is basically my key. I was using Cami to do this. So actually this is green and it's larger. So that it's easy to tell the difference between what's water and what's the sugar. And the sugar, the solute, which is being dissolved, I made smaller and it was blue. Okay, so as you can see from this is pure water. It does not have anything mixed in it. Okay, here what happens is I have the same amount of water. So here I had actually just put 10 molecules, all right? So I put another 10 here, 10 molecules of water. And here I also have 10 molecules of water, trying to evenly spread everything out. Since remember again, with a solution, it's a homogeneous mixture. So your solute and your solvent should all be, well, your solute should be evenly distributed throughout your solvent. Solute, in case I didn't say it right, solute should be evenly distributed throughout the solvent. Okay, so here, dilute is less. Okay, remember there's less solute dissolved in the solution. So here I only put 5 particles of the sugar, all right, 5 molecules of sugar. Concentrated means you're going to have more solute, more sugar dissolved into that water. So what I did was, to represent that, I put more molecules. Notice again, I tried to evenly distribute it because it's supposed to be homogeneous, evenly spread out. So try to keep your space in between. You don't need to count this out. We're just showing more and less. So I just put them, the dots in for the sugar and just tried to make sure they were evenly spread out. The only thing I made sure to do was make sure that the concentrated side, the concentrated solution, has more solute, more sugar dots here than in the dilute solution. All right? So the next thing down here says, well, what if instead of trying to drop particles, what if you were looking at solutions themselves? Is there a color difference? Can you tell the difference between Kool-Aid that is dilute and Kool-Aid that is concentrated, or coffee that is dilute and coffee that is concentrated? So in this case, what we're doing is we're looking at dilute and concentrated solutions, but what I did was I put just used blue food coloring and I put it in water, all right? So trying to look at the difference between concentrated and dilute, and here are the results. All right, here is one solution. And here's the other one. And it is the exact same amount of water. There are 200 milliliters in each of these containers. Let's see if I can do this. All right. So if this is container A, 200 milliliters of water in each container, all right? One has more solute, one has more food coloring, the blue food coloring. They both have blue food coloring, but I use more in one, more solute, which means it is more concentrated than the other. So can you tell which one is more concentrated and which one is dilute? Dilute means it has less of the food coloring. It has less solute, all right? Okay, so the answer would be A. A is dilute, sorry. This is the more concentrated one. B is more concentrated. I put more food coloring in there. Okay, so there's more solute in this. And B is the one that's dilute. So when you see these things, when you see them, as far as a mixture, you can usually tell by coloring, all right? So as far as this one that is dilute, it tends to be lighter in color. The one that is concentrated tends to be darker in color. And it's more translucent, which means it's easier for, not so much of the light is blocked, all right? So it's easier to kind of see through this than it is to see through the one that is more concentrated, all right? So to represent this using the picture or the box below, all right, what we did in class was we took blue. So in Cami, go to your drawing tool and use blue ink. We used a darker blue for concentrated, colored that box in with darker blue, and then chose a lighter color of blue to represent the dilute solution. And then just on the bottom, we wrote, so take note, darker solutions tend to be more concentrated. They have more dissolved solute. Dilute solutions tend to be lighter in color and also more translucent, all right? Allows more light through than darker solutions. All right, and then the next part said, again, if you need to pause it to get this down, please do so. Describe the dissolving process. Be sure to use the words random molecular motion in your explanation. So particles, remember that particles are in constant random motion, all right? That would be your molecular motion. So there is random molecular motion. It doesn't matter if, so solids and liquids mainly are moving around each other. They're fluid, they're able to flow over each other. So think of it, solids, they are more stuck in place, more rigid because of the stronger bonds. They're vibrating. So all particles are always in constant motion unless you're at absolute zero, and that's where all motion, even vibration, stop. All right, so mainly the particles are in constant random molecular motion, all right, moving around. So think about these molecules as they're moving around, they tend to bump into each other, all right? They have an energy. The more energy they have, the faster they're moving, and they're going to be bumping into each other a little bit harder. So when a solute is added to a solvent, the solvent molecules, such as water, bump into the solute molecules, and it's going to break them apart. And then as those particles are broken apart, the solute is broken apart, they spread evenly throughout the substance, which is called what kind of solution now? Since it's evenly spread throughout, what's the word? Homogeneous. Okay, so this is how your homogeneous solution is being created. So taking one more look at the water here, beaker of water. Okay, what I'm going to do is I'm just going to put a drop of food coloring in here, and I want you to look at the motion. Okay, so look at that as it's going down. You see it's spreading out, all right? So what is making it move around and spread out? That is the water. The water molecules are moving randomly about, bumping into the solute, the blue food coloring, and it's causing it to spread out. So it's breaking it apart and spreading out. Eventually what's going to happen is this is going to be evenly spread out. But at this rate, as you can see, it's going to take a while. Now, are there things that I could do in order to speed this up, to speed up this process. All right, so before we get into that, that would be the next page. There's one last piece down here that you need to fill in, and that is the definition of solubility. So solubility is the ability of a solute to dissolve in solution. So sometimes you can dissolve more solute into solution, and sometimes you're going to be able to dissolve less. Now, soluble means it can be dissolved. Insoluble are things that cannot be dissolved. So like oil and water, do they mix? They don't mix. You do not have oil dissolving into water. So that would be saying that, not saying that oil can't dissolve in anything, but as far as water, it will not dissolve in water. So oil is insoluble in water. Kool-Aid, on the other hand, sugar and salt are soluble in water. But as far as that ability to be dissolved, that solubility, there are factors that will affect it. So what are those factors? So I was looking at this. Remember, we're looking at this. And I was saying, see, it's moving, it's getting there. It's not completely evenly distributed yet, all right? But there are things that we could do to actually get this moving along. So what are some of those factors that would affect solubility, all right? And that is on your next page. So here, specifically for solids, we're looking at how temperature, pressure, and surface area affect solubility. All right, so for solids, increasing the temperature or stirring. So we know that if I stir something up, it's going to make it dissolve faster. If I increase the temperature, that will also help it to dissolve faster, but it will also increase the solubility of a substance. So that means you can actually dissolve more solute into the solvent. So what happens is, like salt, if I put salt in cold water, I can put a little salt, but eventually what's going to happen is you'll start to see some of the salt just settling on the bottom, all right? So it stays in the solid form. But what happens is if you heat it up, more of that salt will dissolve in the water. So you've increased the solubility by increasing the temperature. Okay, so also what affects the rate? So increasing the temperature will increase the solubility, and it increases the rate of that dissolving process. Stirring will increase the rate of the dissolving process. Your surface area. So increasing the surface area this is going to sound strange, but to increase the surface area, increase those objects that have a larger surface area means it's looking at in comparison to how much volume they have, how much space they have inside. So actually, the smaller the object is, the greater the surface area it has, okay, in relation to its volume. So when we say increase the surface area, we're talking about actually making the particles smaller. So that will increase the solubility, all right? So if I use granulated sugar, the little grains, I get a teaspoon of sugar with all the little teeny tiny grains of sugar versus a sugar cube, okay? Which one is going to dissolve faster? Well, that would be the granulated sugar, because remember that the water is moving around. It's basically beating up, okay, colliding with the sugar, and it's going to cause it to break up. Well, it's easier to break up, and it's going to be faster breaking it up with granulated sugar because the pieces are already small. With a sugar cube, you have particles of sugar that are surrounded by more particles, So basically what happens is the water has to dissolve the outside, break up the outside before it can get to the inside. So it has to work from outside to inward. That's going to take a longer time. So the larger the surface area, the faster it's going to dissolve. And then as far as a change in pressure, that is not going to change the solubility or affect the rate of dissolving for solids. Now, on the other hand, gases are different. So such as carbon dioxide. Carbon dioxide is dissolved in soda. So if you increase the temperature, of the liquid. Soda, remember, is mostly water. So your solvent is going to be water. So if you increase the temperature or stirring it, actually, you're speeding up the particles, giving it more kinetic energy, which means you're increasing the temperature. So stirring is a way of increasing temperature. It's just not as rapid. Okay, but what it does is it will decrease the solubility. So whereas solids dissolve best in higher temperatures, your gases dissolve best, means they stay in water. They dissolve best in water at lower temperatures. So cold water holds onto gas better than warm water. So doing things such as your soda, if you buy a 2-liter container of soda and you open it and you drink some, close it up, it is better for you to store it in the refrigerator, keep it at a low temperature, and it's going to hold on to that carbon dioxide a little bit longer. So we know that eventually what's going to happen is that soda is going to go flat, okay? And every time you open up that bottle, you hear gas escaping, because what happens is the carbon dioxide that is in the soda liquid itself, is going to escape out, and it sits in that empty space at the top of your container, your 2-liter container, and as soon as you open the container, that gas escapes. The thing is, if you store it in the refrigerator, the rate at which that gas leaves the liquid is going to be a lot slower. If I store my soda out on the countertop in my room, okay, in my kitchen, what's going to happen is I'm going to lose gas out of that soda faster, which means your soda will go flat much sooner. Surface area, I didn't find much information on them. Actually, I found kind of contradicting information, so we're not going to look at that. And then we have increasing pressure, which is like your atmosphere, so I'm pushing down. So remember, with gases, they're trying to escape into the atmosphere, just like water boiling. The more pressure you put on it, the more energy it's going to need in order to for that liquid water to turn into water vapor, okay? Because it's basically pushing out against something that is pushing down on it. So that is why at sea level, or down here where we are in the valley, the boiling point of water is 100 degrees, whereas if you're up in the mountains, the higher up in elevation you get, the lower the temperature has to be. It does not need to be at 100 degrees to boil. It can be at like 70 degrees to boil, all right, if you're high up enough, all right, because there's less pressure there. Well, it's the same thing with gases sitting in a liquid, all right? So the less pressure you have on it, the less pressure, that means the easier it's going to be for that gas to escape out of the liquid. The more pressure you have, it's going to hold on to that gas a little bit better. So in terms of my soda not going flat, living down here in the valley is good. Okay, it's going to hold on to its carbonation just a bit longer. All right, that concludes it for our notes. If you have any questions, students of mine, please come and see me, and be sure to study this and be ready for the quiz. Good luck.